Hello, welcome to chapter 10. After learning about covalent bonding and ionic bonding, it's time to learn about the molecular shape, because in the previous chapter you did not work with real shape of the molecules. You just ended up with drawing the molecular structures, like Lewis structures, right? Remember? So in this chapter we're going to talk about the molecular geometry and the chemical bonding theory or theories. There are three theories about the chemical bonding. Valence shell electron pair repulsion, or VSEPR, is the first one. The second one is valence bond theory, and the third one, the last one, is molecular orbital theory, or we call it MOT. So in each video for this chapter, I will try to explain each of these theory. So the first part, we work on the valence shell electron pair repulsion, or VSEPR. Valence shell electron pair repulsion. It determines the molecular shape. It's based on this concept that the bonding pairs, bonding and non-bonding pairs, of course, the electrons around central atom are oriented in a way to minimize the repulsion, because bonds and non-bonding electrons both are electrons, right? They have a repulsion towards each other. So the orientation around central atom in a way so the repulsion is minimal. So I'm going to emphasize on some specific shapes. There are more shapes and molecular geometries you will see on your book and on your PowerPoint slides. I basically emphasize in the test, I will emphasize in these shapes that I write on the board, and I have already on the board. So let's start with the simplest one, with the smallest one. I have made a little molecule for you. I don't know if you can see it in from this distance, but hopefully it's clear. Let's say you have a molecule like Bcl2. If you remember, beryllium was one of the exceptions to the octet. It's okay with 4 electrons around it, or 2 pairs only, 2 bonds. So if you have such a molecule, let's determine the number of electron pairs around central atom. So whatever I talk about is about central atom, okay? So we have 2 pairs, both of them are bonding. B stands for bonding, and 0 non-bonding. NB means non-bonding. I don't have enough space, so I just had to write it as B and NB. So one more time. In the molecule like BeCl2, beryllium chloride, there are 2 bonding electron pairs, you see the bonds, and no non-bonding, okay? So what do you see? You see a line, right? But you need to be able to determine 2 things: electron geometry and molecular geometry. So what is the difference between electron geometry and molecular geometry? Let's add it to our table that electron geometry is talking about bonding electron pairs plus non-bonding electron pairs, okay? So bonding plus non-bonding electron pairs. But molecular geometry is just talking about bonding electron pairs, okay? So in a molecule like beryllium chloride, you only have 2 bonding pairs, right? There is no non-bonding pair. So this non-bonding pair here is 0, right? So I expect the electron geometry and molecular geometry be the same, because both of them just have bonding electrons. When you have 2 bonding electrons and no non-bonding electron pair on it, you see a linear for both electron geometry and molecular geometry. If you would like to work more with the molecules and you don't have access to the molecular kits, you can just work with the balloons at home. Try to tie 2 balloons to each other to create the 2 atoms around central atom, and then the middle of the balloons will be considered as central atom. So you will see, if there is nothing else around them, these 2 balloons are going to stay in a linear shape. When you have a linear shape for your molecule, the bonding angles are 180 degrees. You need to memorize it, and it's let's say you need to learn it, because if you know that there are two bonding electron pairs and no non-bonding, automatically linear shape comes to your mind. All right? So let's go and increase the number of electron pairs around our central atom. What if you have 3 electron pairs? All of them are bonding again, no non-bonding, like such molecule like this. I hope it's clear from this distance. Like BF3. Boron was another exception to the octet. So let's see, when you have 3 bonding pairs and no non-bonding pairs, again, no non-bonding pair is 0. So electron geometry must be the same as molecular geometry. Do you see a triangle? So it's a triangle, but it's flat, right? So you call it trigonal planar. We're expected to know the name of the molecules correctly with their correct spelling. So it's a triangle, it's trigonal, but it's flat, so we call it planar. Right? Okay, so let's add one more electron pair, like in CH4 molecule. Remember, CH4 was the very first molecule that we drew last chapter. So here are 4 bonding pairs, and again, no non-bonding pair. Now again, electron geometry will be the same as molecular geometry because this term is 0. So we call it tetrahedral. Tetra means 4 and hedral means side. So it's a tetrahedral molecule. 1, 2, 3 towards me, and the 4th one on the bottom of the molecule. So 4 sides for this molecule is called tetrahedral. And for a tetrahedral molecule, the bonding angles are 109.5. So the bonding angles are not 90 degrees. Why not? Because 90 degrees creates too much repulsion. So you see, by increasing the number of electron pairs, the bonding angle decreases from 180 to 120 to 109.5. I'm going to add 2 more to this table, so allow me to erase these 2, and you will see the difference between what I have on the board and what I'm going to add. All right, let's take one of these bonds out, and I have these little wings here, which are supposed to be our non-bonding electron pairs. Non-bonding electron pairs are not confined in a bond, so they occupy a larger space. All right? So we have 4, let me change it, 4 electron pairs. 3 of them are bonding, and 1 of them is non-bonding. 3 bonding and 1 non-bonding. For electron geometry, we are supposed to consider both bonding and non-bonding. So 3 bonding plus 1 non-bonding, you still have 4 electron domains, 4 electron groups, right? So your electron geometry is still tetrahedral. Okay? Ooh. All right. I'm supposed to fix this. All right. Now, as far as its molecular geometry, I told you just to look at the bonding electrons. So let me cover this non-bonding pair. What do you see? Don't you see a pyramid? I hope you do. And the base for this pyramid is trigonal, is a triangle. So we call it a trigonal pyramidal. Trigonal pyramidal. When you had only 4 bonding pairs and no non-bonding pair, what were the bonding angles? 109.5. Now this non-bonding pair exerts more repulsion. So it squeezes the bonds a little bit more towards each other, and bonding angles instead of 109.5 will be 107 only. Okay? And let me fix these table. And the good example will be ammonia molecule, NH3. So by substituting the bonding electrons with non-bonding electrons, bonding angles decrease because this non-bonding pair exerts more repulsion. It's a bigger electron domain. And finally, I'm going to replace one more bonding electron pair with one more non-bonding electron pair. Let me do it with the other wing I have here. All right. Our molecule will be something like water molecule. Two non-bonding pairs on oxygen and hydrogen. You worked on all of these in the previous chapter. We drew all of the loose structures. So, electron geometry, both bonding and non-bonding. So you still see total 4 groups, right? 2 bonding, 2 non-bonding. So you still have 4. Your electron geometry is still tetrahedral. It doesn't change. But as soon as I cover these non-bonding pairs, what do you see for the molecular geometry, the bonds? Don't you see a bent molecule or a V-shaped, right? It's not like an upside down V. And we call it bent or V-shaped. And as you saw, by replacing a bonding pair with a non-bonding pair, the bonding angles are going to be smaller. We expect these bonding angles to be less than 107. The bonds are more squeezed, so the bonding angle is going to be 105 degrees. So you remember we started from 180 degrees, and now we have only 105. All right? I hope you learned. Again, if you have any problem understanding, just use the balloons and try to tie them together. You will see the actual shape easily with the balloons. 2 more molecules I want to talk about. You have them on the PowerPoint slides. I just wanted to mention it. When you have Pcl5 and Sf6, again, exceptions to the octet rule, they're extended octets. So, you see, it seems like you have 3 phosphorus atoms. Unfortunately, I didn't make them with the molecular models, but that's okay. There are 3 phosphorus atoms on the same plane, and 2 of them are on the top and bottom sticking out. So, such a structure is called trigonal bi-pyramidal. I don't know if you can see a pyramid on top. I tried to show it. A pyramid on top and a pyramid on the bottom. Do you see it? And it looks like they are trigonal, which are sticking to each other from the base, right? So 2 pyramids bi-pyramidal, which are trigonal shaped. So trigonal bi-pyramidal. It's good to know about this molecule. The bonding angles are different because you have a triangle, which are 120, and you have this bonding angle here, bonding angle between chlorine and chlorine from top to bottom, which is 180. So forget about it. The bonding angles are a little bit confusing because there is more than one bonding angle involved. The second exception to the octet, extended octet, was Sf6. So it looks like the base is a square, and again you have 2 pyramids, right? But such a shape will be called an octahedral. Octa means what? Means 8, right? So octahedral means there are 4 sides on top. There is a tetrahedral on top, and there is a tetrahedral on the bottom. So 4 and 4 is octahedral. These 2 exceptions are very famous, so don't worry about the rest of them that you have on PowerPoint slides and in your book, which are called like T-shape or seesaw. They're not very important. I'm not going to focus on that. If you learn these, you know more than enough for this level. The very last thing in this part, in this theory that I would like you to know is that you draw the structure for carbon dioxide and you had two double bonds, right? I want you to know that double and triple bonds don't have any role in the shape of the molecule. So whenever you want to determine the shape of this molecule, simply ignore these double bonds, okay? So let me draw it with different color. Oops. Just ignore these two blue bonds. What else do we count? This bond, which is called sigma, and this bond, which is called sigma. So every single bond is called a sigma bond. So you only have two bonding electron pairs, and you remember we had a linear shape with 180 degrees angle. This is 180 degrees. So at the end of this part, let me tell you, a single bond, as we label it right now, is called sigma. This is a lowercase sigma. So a single bond has one sigma bond. A double bond contains, as you see here, one sigma bond and one pi bond. So this is called pi, this is called pi. In the next video, when we talk about the valence bond theory, I will explain the sigma and pi bond more. And in a triple bond, you will have one sigma. In any case, you just have one sigma bond. And what do you expect for a triple bond? 2 pi bonds. So a molecule like HCN, this is one sigma. Oops. One of them is pi, another one is pi. So how many total sigma and pi bonds do you have in a molecule like HCN? 2 sigma and 2 pi. I hope this first bonding theory was useful and helped you to learn. In the next video, I will talk about the valence bond theory. Don't forget to have enough practice.